Okay guys, in this lesson we're going to be talking all about falling under gravity. So this is quite a quick but important thing to think about. So this is on your whiteboards because it's taken from a lesson, but I just want you to imagine here in each of these pictures somebody's holding a ball. What direction will the ball fall in if they let go? Well, hopefully you can see for this top one it will fall straight down towards the centre of the Earth, and for all of them that will be the case. Gravity always acts towards the centre of Earth. But generally speaking, we think of Earth as being flat. Now, I'm hoping that my YouTube channel is not about to get inundated with flat earthers, because the world is a globe, it really is, anyone else is just wrong. But generally we act as though weight or force just goes straight down. But there's a reason for that, and that's because it's actually acting towards the centre of the Earth. If you think about it, it makes total sense, otherwise people in Australia would be floating off into space, and that doesn't happen. So, hopefully this is a recap for you, but we do come across it a lot. You need to understand the difference between mass and weight. So mass is the amount of matter, it's the amount of stuff in an object, and it has the units kilograms. Weight is the force of gravity pulling an object down, and it has the units newtons. And this is really confusing because generally in life people don't ask what is your mass, people ask how much do you weigh, and you use a weighing scale to find the mass of something. It's all a mess. Now the reason for that is generally in life we actually measure mass using weight, because generally what we do on a weighing scale is you've got a spring, and when you step on it you're compressing the spring with a force of your weight, and we know that the more mass you have the more weight you have, so we kind of calibrate it in weight. But it's not true. Really, your weight is your force of gravity pulling you down. Your mass is how much stuff you have. So let's think about gravitational fields. Hopefully you've seen lots of times before. If I have a 10 kilo object, so its mass will be 100 kilos. A 100 kilo object on Earth has a weight of 100 newtons. So mass is the amount of matter, the amount of stuff that's there. The weight is the force. If I have a 5 kilo object, it'll have 50 newtons. And if I have an 800 kilo object, it'll have a weight of 800 newtons. So what you can hopefully see from this is that each kilo of mass on Earth is pulled towards the Earth by 10, whoops, let's change the colour, 10 newtons. So what I can say about that then is I can give it an idea of gravity, and I can say gravity is 10 newtons per kilo, and in science we give that a symbol of little g, and it's just 10 newtons per kilogram. With that, if I call mass m and I call weight w, I can say that weight is equal to mass times gravity. Yeah, it's always mass times 10. Why do I want to use little g and not just the number 10? Well, the reason is that on different planets I might have different strengths of gravity. So on the moon, for example, you see people bouncing around. That's because gravity is much weaker. So the force on each kilo of someone's mass is much less. So I'm going to number these sentences 1, 2, 3, and 4. And I want you to tell me which ones are correct. Well, I used the scales and found that I weighed 65 kilogram. Weight is a force. Kilograms is used to measure mass, so this is not correct. If I said I used the scales and found my mass was 65 kilograms, that would be correct. So my rucksack felt heavy. When I checked it, it had a mass of 30 kilograms. Kilograms is the unit of mass, so this is correct. The mass of my dog is 200 newtons. Well, newtons is the unit for weight, as it's a force. Mass is an amount of stuff, so it's wrong. Yeah? We could say the weight of my dog is 200 newtons. And the weight of my hamster was only 8 newtons. As I said before, weight is something that we measure in newtons, so that's fine. And 3 was wrong. This is a real key thing here. How fast should I fall? So I want you to imagine I've got an object here and it's got mass m. How fast is it going to fall? Well, I now know that the force acting down on it, the weight, is equal to its mass times gravity. But I also know that the acceleration due to a force is mass times acceleration. Now what do you notice here? What I notice is that I've got a force acting on my object and a force acting on my object. And in this case, those two big F's, are the same. So I can say, therefore, that F is equal to ma, which is also equal to mg. Now looking at those, I can divide both sides by m and cancel it and get acceleration is equal to g. So all objects should accelerate when I drop them. If I take my pen and drop it, it should fall accelerating at 10 meters per second squared if I'm on Earth. Now, is this always true? Actually, it's not. Because let's imagine that my object is already falling. Whee! If it's already falling, then what happens to it? Well, as we did last lesson, well, a couple of lessons ago, it will start to get air resistance, Fr. So now, the overall force on my object is not ma, the force due to gravity is mg, but I will actually have a force on my object of equal to mg minus the friction force, the air resistance force. And when that's the case, I can no longer say that this F is equal to this F. They're not equal, so this doesn't work anymore. But we'll go through some specific examples of that in the lesson. Okay, that was quite a lot. Hopefully we will consolidate that, but hopefully you just got that fresh in your mind for the next lesson. Join us next time when we're going to be talking about Newton's laws.